Let's look at stretching and compressing the absolute value parent function. So you see I have the parent function y equals absolute value of x, the table of values for that function, and a graph of that function. And what I'm going to do is I'm going to plot points to graph y equals 3 times the absolute value of x. Okay, so let's start plugging in these x values. When I plug in x as -3, I have 3 times the absolute value of -3, and we know the absolute value of -3 is 3, so this is going to be 9. Plugging in -2, this is going to end up being 6, and this will be 3, because 1 times 3 is 3. 0 times 3 is 0. And you can plug in these values or use the symmetry of the absolute value function to know that the next values are going to be 3, 6, and 9. Okay, let's plot these points on the graph, and I'm going to start plotting from the vertex. So I'm going to start at 0, 0 and plot points to the right of the vertex. The next point is 1, 3, 2, 6, and 3, 9. To make this a little easier to communicate, I'm going to refer to the graph of the absolute value function of absolute value functions to the right of the vertex as the right-hand branch of the graph. So I'm going to call this the right-hand branch of y equals 3 times the absolute value of x. And now I'm going to graph the left-hand branch of y equals 3 times the absolute value of x by plotting the points to the left of the vertex, which are -1, 3, -2, 6, -3, 9. So again, I'm just referring to this as the left-hand branch of the absolute value function to make communication a little easier. All right, let's see. Hopefully those line up. There we go. So we have the graph of y equals 3 times the absolute value of x, and the first thing you should notice is that this graph is more narrow than the original absolute value graph, y equals absolute value of x. It's been stretched, it's the parent function stretched vertically, meaning if I wanted to make a transformation to the absolute value parent function y equals absolute value of x to obtain the image y equals 3 times the absolute value of x, I would stretch the parent function vertically by a factor of 3. Okay, that's should be pretty clear from the graph. Now I'm going to talk about something else. If you look at the right-hand branch of y equals 3 times the absolute value of x, you should notice that it has a slope of 3. So if you go from one integral point to another integral point, you'll get there by going right 1, up 3. So I'm going to denote that by m sub r, meaning the slope of the right-hand branch of the absolute value function, and its slope is 3. And alternatively, on the slope of the left-hand branch, you'll notice that the slope is -3, meaning to get from one integral point to another, I could go down 3, right 1. Also, you could go the other way. You could go left 1, up 3. Either way, you'll still have a slope of -3. Okay, so a couple things we noticed here. It appears that the slope of the right-hand branch is equivalent to the number being multiplied by the absolute value function. And it also looked like that multiplying the absolute value function by this number stretched the graph vertically. Take a moment and graph the following function by plotting points. Y equals 1/2 times the absolute value of x. Plot some points and then put the graph the function. When you come back, I'll have that up and we'll have a discussion about that. Welcome back. If you graphed the absolute value function y equals 1/2 times the absolute value of x using the same x values in your table as mine, this is what your table should look like. And no matter what values of x you chose, you should have graphed an image that looks similar to this absolute value function in green here. And the first thing you should notice is that this function is wider than the parent function y equals absolute value of x. And what happened here was to obtain this new image, you would compress the parent function y equals absolute value of x by a factor of 1/2. Another thing you should notice is that the slope of the right-hand branch is 1/2, meaning to get from one integral point to the next, say the vertex to 2 comma 1, we would go right 2 up 1. And for the left-hand branch, you would obtain a slope of -1/2. So you can try out a few more values of a being greater than 0, and you're going to reach this ultimately reach this conclusion. Given that a is greater than 1, if a is less than 1, the graph of y equals a times the absolute value of x is the graph of the parent function compressed vertically by a factor of a. That's what we saw here in this 1/2 case. We compress the parent function by a factor of 1/2. If a is greater than 1, the graph of y equals a times the absolute value of x is the parent function stretched vertically by a factor of a. That was what we saw in this case, y equals 3 times the absolute value of x, where it was stretched vertically. And one extremely important observation to make is the slope of the right-hand branch is a, oh, get rid of this. This doesn't belong. The slope of the right-hand branch is a. Given that y equals a times the absolute value of x, the slope of the right-hand branch is a, and the slope of the left-hand branch is -a. So I'm going to use this information in particular to graph y equals 2/3 times the absolute value of x. This is a key observation for graphing absolute value functions. And then I'm going to make an observation, confirm this observation from the graph. So to plot this, I'm going to start at the vertex, which is 0, 0, and that's because this graph has not been translated left or right. There's videos on vertical and horizontal shifts in the link in this video. So I start at the vertex 0, 0, and I know the slope of the right-hand branch is going to be 2/3, which is a. So I'm going to go right 3, 1, 2, 3, and up 2, 1, 2. And that should give me the graph of the right-hand branch. Ooh, I went right 3 and up 2. This is off a little bit, huh? Let's pull this down just a little bit. Okay, there we go. There's our graph. And similarly, on the left-hand side, the slope of the left-hand branch is -2/3. So I'm going to start at the vertex. I'm going to go left 3, 1, 2, 3, and up 2, 1, 2. And we will see this is the graph of y equals 2/3 times the absolute value of x. Now, if you want to, you can confirm this by plotting points, but this is correct. And another thing that we want to comment on here is that 2/3 is greater than 0 and less than 1. So this is the graph of y equals absolute value of x compressed vertically by a factor of a, meaning it's going to be wider than y equals absolute value of x. And you can see that if you imagined the y equals absolute value of x graphed on this same image, you would see that it would be narrower than y equals 2/3 absolute value of x. Okay, what I want you to do is take these three functions and graph them the same way I just graphed y equals 2/3 times the absolute value of x using this given information, and then comment on is the graph compressed or stretched. For instance, in the example I just did, this was a compression. This is a compression of the parent function. Pause the video, answer these three, and you come back, I'll have the answer. All right, here is the graphs of the three equations and a description of the transformations on the parent function. So y equals 4 times the absolute value of x is the graph of the parent function stretched vertically by a factor of 4. You can see that if you were to plot the absolute value function, y equals absolute value of x, along with this graph. Y equals 3/2 the absolute value of x is the graph of the parent function stretched vertically by a factor of 3/2. Special note here, notice that 3/2 is greater than 1, so this is a vertical stretch. And the final one, y equals absolute value of x divided by 4 is the graph of the parent function compressed by a factor of 1/4. And those are the three answers. Let me know if you got them right in the comments section, and thank you for watching.